Well, now let's take a look at two other questions here, parts E and F. Let's suppose that the company wants to provide a warranty. Now, how many hours should they guarantee that a bulb will last such that no more than 2% will actually fail before the time they guarantee? Okay, so again, I need to read through this question maybe a couple different times and figure out really what it is that they're asking for. If the company wants to provide a warranty, here it is. How many hours should they guarantee? I'm going to be looking for a number on my number line. I'm going to be looking for a value of X. What's the number of hours that should be printed, say, on the packaging that we're guaranteeing to the customer the bulb will last? Okay, so I know I'm looking for a value of X. But now the question becomes, where is this X on the number line? Is it bigger than average or smaller than average? Like below 750, above 750? Where does it fall? Well, I want to be able to guarantee right now that the bulb will last such that, or the hours that it's guaranteed will be such that no more than 2% will fail before the time guaranteed. Okay, so if I think about where my value of X is then, it's probably going to be down here. I would provide a warranty on bulbs that last too short of an amount of time. And the amount of time that we are going to be guaranteeing is before our X, and we want that to be worth 2%, or 0.02. Okay, so the company says, I'm going to guarantee you this amount, and then I want 2% of things will actually be able to, apply for the warranty or get their product replaced. So I need to find that X. And how do I find my green X? What calculator command can I use? Well, I should be able to use inverse norm. I start with area to the left. Remember, you should write that as a decimal in there. And then 750 and 10.6. If I was to go to my calculator to crunch this out, the value that I get back is something like 728 point, not 0.0, 0.2303. You could confirm that that is actually correct. So apparently the company should be guaranteeing roughly 728.2303 hours. Now you could probably think from like a company point of view, that's a really awkward number to put on your packaging, right? Like could you imagine like going out to Menards or Home Depot or something today, like looking at a light bulb and like looking at the packaging, spinning it around and seeing, we guarantee that our bulb lasts 728.2303 hours. Usually we're going to probably round that off to a whole number amount. But which way would the company round? Would they round that up? Would they round that down? Well, notice that I'm not actually going to answer that question by thinking about traditional rounding rules. Because the goal here is that when I move my X either up a little bit or down a little bit, that is rounding it up or rounding it down, I want to guarantee that no more than 2% is going to get shaded. So which way do I have to move my X, rounding down or rounding up, so that my blue space is not going to end up more than 2%? Well, in this case, it just happens to be that I would end up rounding it down. Notice that if I was to kind of slide my X over to make a new X, if I went down, I would have something a little bit less than 2%, which is exactly what I want. If I moved up a little bit, I would shade more than 2%, which apparently is not okay. So I can say here that the company should guarantee 728 hours. That seems to make sense. That would allow me to move down a little bit and still make sure I didn't guarantee more than 2% of bulbs or provide a warranty for 2% of bulbs. Okay, let's take a look then at part F. Notice here, what are the quartiles for the distribution of lifetimes? The quartiles? We haven't talked about quartiles for quite some time, but they actually apply here very, very simply. Let's see what we have. Again, I'm going to sketch out my nice distribution. 750 in the middle, standard deviation of 10.6. Now once I have this, I should know some things about where quartiles number 1, 2, and 3 actually land. In fact, I think I already have one of those quartiles already pictured. I know that quartile number 2 is the median, and that should be dividing the data set in half. So actually, isn't 750 the same as quartile 2? Isn't that exactly the median? It divides the data set into 50% of stuff on the low end and 50% of stuff on the high end. I then know that quartile number 1 should be somewhere over here, and quartile number 3 should be somewhere over here. And I know something very specific about them. If I was to shade to the left of quartile number 1, I know that I should get 25%, because it splits things up into quarters. I know that if I shade to the left of quartile number 3, I should get 75%. So finding all of these values actually becomes extremely simple. Let's try to find each of them rather quickly here. Q1. To find Q1, I would set up an inverse norm. Again, I'm looking for just a number on that number line. There is 25% to the left of it. 750 is the average. 10.6 is the standard deviation. If you type that all into the calculator, you get a number like 742.8504 hours. And that, of course, should make sense. It should be something below 750. We already said here that Q number 2 is super easy. That is just going to be 750 hours. You could do an inverse normal with it. You would just do a 50% is shaded to the left. Of course, that seems like more work than necessary since we already have that value shown in the picture. To find Q3, I'm going to do an inverse norm, and there is 75% to the left. There's then a 750 and a 10.6. If I type all this into the calculator, I think I get a final answer of 757.1496 hours. So I can easily find all of these. So finding quartiles is fairly easy. But then notice that would mean that finding percentiles would also be fairly easy. If I asked, hey, where's the 30th percentile in this distribution? That wouldn't be difficult at all. That would just be an x value like this, where when I shade to the left side of it, I would get 30%. So finding quartiles or percentiles is very easy because they all are telling us, remember, how much area is on the left side of that value, which is exactly what we need as our first value inside of our inverse norm calculation.